So resume where we left off in the previous session. The first thing that we saw there was, let's have a recap first. Bit of recap. We learned about random variables. So what we saw is, we saw random variables are functions. Basically, they take input from the sample space and they assign it a real number. So this is what random variables are. So then I said random variables are of different types. So one thing is called as a discrete random variable and the other is called as continuous random variable. So we have continuous random variables. Random variables. We have hybrid also. So we'll maybe in the subsequent sessions we'll also see the hybrid random variables where some part is discrete and some is continuous. And then I said with this discrete, we're taking this discrete random variable, and I said there is an associated PMF, probability mass function, with it. Okay, so which describes how should you assign the probability to the events. If we have a sample space and you define a function onto that, and then you say probability of x taking this value, probability of random variable taking this value is this much. So this is what is called as PMF. Okay, and you can think a random variable is like this. Let's suppose a random variable, if we have an experiment. So associated with the experiment is a sample space, is a set of outcomes. Sample space can be uncountably infinite, it can be countably infinite, it can be finite. So howsoever you want to see it. Let's suppose this is a sample space. Consider now you have a random variable. I said if you have to see the random variable, see it as if you are just focusing on one aspect of an experiment. The experiment is going on and you are not interested in all the aspects, you are just interested in one aspect of experiment. Then you introduce random variables. This is not a new concept, rather a different perspective to look at the same things that we have studied so far. So we'll say x can take some values. In the discrete case it will take discrete values, in the continuous case it will take continuous values. Let's say it takes these 4 values. So now you have the sample space. So sample space, as I said, can be finite, infinite. So now each of this sample space somehow will be given a value. So let's suppose if I make some circles over here. So whenever I say x is taking value 0, let's suppose. So this means there will be a lot of these outcomes possible in sample space which will take the 0. Let's suppose this and this. It takes, they are fulfilling this criteria. When x is taking 0 value, so these 3 outcomes in the sample space take that value 0. Okay. And similarly, if I say x is equal to 1, let's suppose I'll take x is equal to 1. So maybe 1 and this one and this, these 2 things fulfill that criteria where x is taking value 1, and that's how you calculate their probability. So you have sample space and you take a random variable, let's say x, and you see its value, let's say a, and you go to sample space. From this you go to sample space and then you see how many of the outcomes in sample space, if it is a frequent test approach. So how many of elements in the sample space fit this criteria, okay, where x is equal to a, and then from this you assign some probability to it. You assign some probability. So when I write x is equal to a, you go to sample space. So when I say probability of x is equal to a, it's a 2-step process now. The first, you go to sample space, see the outcomes which are fulfilling this criteria, and then you compute the probability of these. Either if they are disjoint, you will just add them up. If they have some overlap, then you will use inclusion-exclusion principle. Then you have all these things that we have discussed in the previous sessions. So this was some brief recap of the random variables. Then we shifted our gears and we discussed about different types of random variables. So there we saw the first type of random variable was called as Bernoulli random variable, and Bernoulli random variable had one parameter, that is this p. So I said, why are these random variables studied? There are a lot of repeatedly occurring phenomena in the life, and somehow we wanted to say something about this phenomenon, and we wanted to have a discussion on something so that we come to conclusions. So we want to make some conclusions, or at least have some notion, have some something built so that I can say something about different phenomena which have similar in nature. So I said one important thing that you will keep on seeing in life is there will be some sort of failure or success. So many of the experiments can be modeled this way. So there is a thing going on, it can be modeled, either it will be successful or it will be failure. So one example I gave is coin toss. Let's suppose coin toss. Say head is success and tails is failure. Similarly, if let's suppose we are having a company, and if your product is good, and then we'll say product is good, it means success, and if product is bad, it means you have failure. Similarly, if let's suppose you are studying probability, and if you understood all the concepts or most of the concepts, so I'll say you are success, you have got success, or otherwise you have failed. Okay. So many of the real world phenomena can be modeled like this, where you have probability of success and probability of failure, and you can either fail or you can either succeed. So what mathematicians thought, we thought, okay, let's do one thing, let's abstract all the details, let's call this as Bernoulli random variable. It has properties. So the first property that we have, first parameter rather, is we have the probability of success, and then how do we define it? We said either it can be successful or it can be, we can have the failure of this. So this is how we model that situation, and then we came up with the PMF. We said what is PMF? Probability of x taking value 0, this is basically failure, this is 1 minus p. So what is probability of x taking value 1, that is success, this is p. This is the parameter that is given. So we defined PMF of Bernoulli random variable like this. So from the Bernoulli random variable we went to binomial random variable. So in binomial random variable, we said now if you perform these trials repeatedly and independently, okay, each of the trial in this is independent and repeated, but each trial is a Bernoulli trial. Okay, in each trial you are getting a success or a failure. So you in that we took example of a product being sold on some e-commerce website like Flipkart, Amazon, and then we saw that if some seller is having 95% of positive reviews, then what is the probability that I will have a positive experience? Probability of me having a positive experience given the data. This is what I'll be interested in. I'll be interested in to compute. And then I said it is like a binomial process. It's like a binomial distribution process. Why? In that I am repeatedly doing Bernoulli trials, because each of the customer, when it is going to buy a product, it is doing a Bernoulli trial. It is buying their product, and if it is getting a good experience, that means success, otherwise failure. So if you do it n times, that means you are simulating a binomial random variable, because we have n trials, and each of these trials is thought as independent trial, and then each of the trial is also a Bernoulli trial. So now then we came up with the formula. So binomial of np, we said it can be thought like this. It can be thought of having a success with, let's suppose if I want k successes out of these, if I want k times that this should be successful, I said this should be a p to the power k, because this is the success rate, and 1 minus p to the power n minus k. So this is success and this is failure, and then I know that there are different combinations possible, so this will be nck and choose k. Okay, now there are different ways of looking at this. So how can you do? You can directly count you can count the success, number of successes in independent trials directly, and this is how we can count it. Like, let's suppose you count it like this way. Or the second thing is you can introduce an indicator variable. Okay, there is something called as indicator variable. Indicator variable. So indicator variable is a variable. If there is success, it takes value 1. If there is failure, it takes value 0. So how can you express it? Let's suppose you have random variable x. You want to see how many successes are there. Initially here you can directly count number of successes. You can, let's suppose this is first approach where you use this formulation, and the second is indicator variable, where you say that x will have k number of successes. So what you will do is, so you will say, let's say I have a variable I which takes a value, let's suppose I should take some other value, let's suppose we'll take small x. So xi is an indicator random variable. So xi will be 0 for failure, and xi will be 1 when it is successful, and I means ith trial. So I here indicates ith trial. So if I have to, if somebody asks me in a binomial random variable, if there are done n trials are done with probability p of success, so what can you say? How many is it possible that we'll have k success? So what we'll do is, so we'll say xi plus something of this sort. So xa will take values x1 plus x2 plus x3. These will be the number of successes in n trials. So the question will be asked number of successes in n trials. So we'll say x1 x2 till, let's suppose, xn. So where you saw the definition is over here. So if it is a failure, you will say 0. If it is a success, you will say 1. You will just keep on adding these. You will get to know the number of trials in which we had the success. So this is the number of. So here this is also the we assume that we have k successes, and this is the probability it is giving. So here we assume that these many number of times will be successful. Okay, so one is directly, so even I can write third method, which is quite easy. You can really count successes. So this is just mathematical way of counting by using the indicator variable. So this indicator variable we'll use it a lot. That's why I just introduced it. not a new concept. So I said there are three ways to look at this binomial distribution. The first way to look at it is directly go with the formulation. If somebody says I want k successes in n trials, so what's the probability? So you can directly say probability. So if somebody says that if you have n trials, so you want to count how many number of successes there are, so you can just introduce a random variable that's called as indicator variable rather. So and then where if you have this xi, if it's equal to 0, then you'll say failure. If xi is equal to 1, then you'll say it's a success. And then you just count these number of ones. So this will give you the number of successes in these n trials. Or otherwise you can directly count it without having these indicator random variables. Okay, and this over here is called probability mass function of random variable, because this is assigning probability, the first one. This over here is called the probability mass function of binomial n comma p. So this actually is this is not just one distribution. This is a class of distribution. Why a class of random variables rather? Because you can change this n and p. So on different n and p, this will become a different class. But this can be studied under the similar set. We saw a simulation of this also. So we saw if we have to compute it like this, so we can make a simple simulation and ask it if I am having now, let's suppose 50 customers are there, and I know, like suppose success rate is assumed to be 0.95. So is it possible that I'll have 48 good reviews and 2 bad reviews? Okay, we saw what's the probability of that. We saw it is basically a distribution of this sort. Okay, where you have distribution, and on changing this n and p values, you are seeing that this distribution was getting shifted to left to right, and it was like accordingly changing based on these n and p. So that's why these things are called as parameters. So this n comma p is called as parameters of binomial. Okay. Now let's do some questions so that you understand why are we studying. I'll take some real world examples, and then you will reason about the examples. You will try to come up with the answer, and before answer you should at least come with the understanding. How can I understand? How can I model it by using random variables? As I repeatedly said, this random variable, this is not a new concept that you will be learning. You are not learning something new over here about probability, but this is just a new perspective, or just putting it this is giving you a language, because as I say, mathematics is a language. So you are having now more tools of that language. So in order to communicate, in order to make your life easier to perform this algebra or to perform the mathematical operations, it is sometimes becomes easier to look the problem in a different perspective so as to solve it. You will start with a simple problem. So there are 5 fair coins. So we have 5 coins. All of these coins are fair. So and the outcomes are assumed to be independent. So you have to find the probability mass function. You have to find probability mass function of this. Okay, this is the question. You have 5 fair coins, and each coin, by fair I mean probability of head is equal to 0.5 and probability of tail is equal to 0.5. Okay, now you have to find its PMF. So how will you compute its PMF? Any thoughts? The first question that you should ask is PMF about what? So what I can consider success over here? Okay, or what should I consider failure over here? Okay, let's say you can consider head or tail. Anything can be considered failure, or anything can be considered success. So in this case, so you'll have to see success as head. If you have head, this is success. So how can you find the PMF of this? Another question that you clearly saw was we had 5 coins and each of the trial was independent, and here the success was considered head. So we just wanted to consider the PMF. So what is the way in which we can construct PMF? The first thing is we have to model the problem. So we'll introduce some variables. So the first variable I'll introduce is x. So x will be a variable which will represent number of heads. The number of heads. So this is a random variable now. The number of heads is represented by this x. The x is a random variable, and this is a discrete random variable per se. So now what are the values that it can take? So we know that we have 5 coin flips. The possible sample space is from all heads to all tails. To all tails. Okay, the total possible outcome is 2 to the power 5, that is 32 elements in this. And if we go with the naive definition of probability, if each of these is equally likely, so for one of these outcomes, the probability is 1 by 32. Okay, so I'm assuming that each of these is equally likely. So x is the number of heads now. The values it can take is 0, 1 till 5. Because we can have 0 number of heads, we can have 1 number of heads, 2, 3, 4, 5 number of heads. These are the values possible. Now in order to construct PMF, because we have to consider a probability mass function. So why is it called a mass function? Because you assume the probability to be the mass, and you have to distribute this mass to the different possibilities. The first possibility is probability x will take value 0. Okay, so in order to solve this, I said when you see x is equal to 0, you go to sample space. You go to the sample space. and you tag it. You see how many of the outcomes possible in the sample space can be tagged under this. Can I tag them 0? So I can tag only this. This can be tagged to 0, and none of the other outcomes in the sample space can be tagged with the 0. So you just see the random variable. From this you go to sample space. So in the sample space you see how many of these satisfy this condition, how many of these can be tagged by this. So you can see clearly. So there is only one element that can be tagged. So you know that if I have to compute the probability, and I'll either use inclusion exclusion or I'll use additivity principle. So now here clearly we only have one outcome. So here the probability is 1 by 32. And now going forward, p x is equal to x is equal to 1. That means probability that this random variable x will take one value, or if I have to speak in pure English, that is the possible number of heads is 2. So when I flip these 5, when I have these 5 trials of flip of a coin, so I want one head. So I want one head in 5 flips of the coin. So now what will I do is I'll again go to sample space. So I'll see for how many cases it's possible that I'll have one head. So I know I can have head, tail, 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 tail. Okay, and then I'll have head, I'll have tail, head, tail, tail, and tail, something of this sort. So I believe there are 5 possibilities. 5, and each of this is having 1 by 32 of probability, so 5 by 32. Similarly, you can compute the probability for probability x can take value 5. That is, the number of heads are 5. So clearly know that there is only one possibility where we'll have all the heads. So you'll go to sample space and you will see how many outcomes satisfy this condition, and then you'll assign probability. So again here it will be 1 by 32. So this over here, if you see this, so where I give all the specification, so this is called as probability mass function. This is PMF. For a random variable, in particular this discrete random variable, we have associated PMF, probability mass function, which defines how can I assign probabilities to different values. Okay, and I told you can also see the distribution like this, because I have distributed this one mass of 1 into these different possible outcomes. So usually it is showing in a graphical way like this. If you see in books, so you'll see a lot of graphs made like this. So where we had values 0, 1, 2, 3, 4, and 5. Now for the 0 you had some probability of this sort, and then for the 5 you also had the same probability, and for 1 you had probability 5 by 32, 5 times this. Let's suppose this is 5 times this. This one is, let's say, 5 times this. Okay, similarly if you have, let's suppose, 4, so you will have some graph over here. Say 2 times means this, something of this sort. Let's say 3 is even, I'm now making randomly, but you got the point. So this over here is called as distribution. So why is it called distribution? So this is probability mass function. This shows the distribution. How was this mass 1 distributed? So we had in total mass 1. We consider that we had mass 1. This was our mass, and we had to distribute it to all possible outcomes, all possible values that random variable will take. So we distribute it in this way. So it made a distribution. So this is what distribution is. Okay. Now with this we can define one more thing. So we have this probability mass function. Now sometimes we'll be interested in what is the probability that here we were taking exactly 1. Let's suppose here we had exactly 0 heads, exactly 1 head, exactly 2 heads. So what if somebody tells me what is the probability this x will take value either 0, or x will take value 0 or 1 or 2, something of this sort. Okay, so mathematically I can write it like this: probability of x will take value less than or equal to 2. That means it can take values whatever came till 2. It can take 0, it can take values 1, it can take values 2. And this is sometimes more useful. Sometimes in order to come up with something, so let's suppose you are working in Amazon. So you are delivering products, and there you want to see what is the probability that, let's suppose we have an x as a random variable, that number of days it takes for a parcel to reach the customer. So you have, for all the regions you have this. So you have this data. So I have this region 1, I have annotated region 1, region 2, region 3, let's suppose region n. So now you have a random variable defined. Let's say x is a random variable, but it defines that the number of days this parcel takes to reach the destination in this particular region. Now you have to be sure that for 90% of the customers, I should be sure. So you are saying probability that, let's say, x will take, for how many customers will it take less than or equal to 5 days? So if this comes out to be, let's say, 95%. So you will be sure that with 95% probability, so let's show the estimated delivery as 5. Okay, you will usually show estimated delivery of 5 days. Okay, because by seeing the data, you are sure that we had the data, and all the parcels, let's suppose we had 100 customers, and for the previous 100 customers, 95% of the customers got their parcel on till the 5th day. Somebody got it on 0th day, that means the day itself. Somebody on the first day, they took 1 day. Somebody took 3 days. But you are having all these possible random variables: 0, 1, 2, 3, 4, 5. Let's suppose the max value it can took so after it took 20. So it can also take some 20 days if the parcel was to reach destination, which was, let's suppose, from the delivery center, it was very far away. Now we want to show an estimate delivery. So what you can do is, from the data you can compute this. You can say what is the probability that within 5 days I can serve it. So you are saying that 95% of the customers are getting served their product within 5 days. So it is a logical and a coherent way of selling. Okay, estimate delivery for you is 5 days, estimate delivery for you is 4 days, and many other times you might have seen that you get your order before the delivery. So it rarely happens that you get your order after delivery. Why? Because they play probabilistically. They define a random variable, and based on the random variable they say what is the probability that this person will receive the order under 4 days. So they basically are computing this variable. Is it clear with the example? Any questions? Okay, now you saw one notion. Why is this thing important? So you can sometimes not just choose a single value, but a value which is in a range. So I want to see what is the probability that I'll get a value from, let's suppose, less than 5. So here we come up with a function which is called as CDF, cumulative distribution function. Distribution function. So whatever we discussed by taking the example of the delivery system, so this is called as CDF, it is cumulative distribution function. So if I say what is probability, this x is less than equal to k, that means what is the in terms of, let's suppose, binomial random variable. So this will mean what is the probability that we will at least have k successes. So we can have 0 success, we can have 1 success, we can have 2 till k successes. So why is it called cumulative? Because we have to sum it up. Okay, so we have to say probability of x is equal to 0 plus probability of x is equal to 1. This is cumulating, so we are accumulating these things. Okay, so till probability of x is equal to k. That's why it's called cumulative. So why distribution? Because it's still showing the distribution. It is still giving you the distribution. And function, because it's a random variable. So we have PMF and we have CDF. So for discrete random variables, we saw two important things. So we saw probability mass function and we saw cumulative distribution function. And we saw the significance of both of these. So if you are given a random variable and you are asked what is the distribution of this random variable, you can either compute this PMF or you can compute CDF. Sometimes it's easy to compute PMF than CDF. Okay, and you can compute CDF from this PMF easily, because if you have PMF you can just add these values up. Okay, so now clearly you can see this CDF over here. The CDF has some properties. It's a non-decreasing function. It's a non-decreasing function. So why is it non-decreasing? Because you clearly know that I'm just adding, I'm cumulating. So it is not possible that I'll add negative value, because probability is not negative. Probability is always positive. So PMF always have properties. So PMF, we have also seen the PMF properties. So for each of this, so probability of x takes a value a, this should be greater or equal to 0. Why? Because I told you it should follow the actions of probability. And one more thing that I said over here is probability of all of these x values, all the values should be equal to 1. This is the properties of PMF. So PMF should follow this property. So accordingly, CDF should have this property. So CDF should be non-decreasing function. It should always increase. Okay. So let's suppose if we have, say, probability of x is equal to 0 is equal to some 0.2, probability of x is equal to 1 is some 0.1, and probability of x is equal 2 is again 0.2. So if you see this function, so this function will look something like this. 0.2 means this much, 0.1 means this much, again 0.2 this much. So this you can see it is increasing, decreasing. This function is like this. So this is probability mass function. Now how can I come up with CDF of this? So I'll just need to add, if I say probability of x is less than equal to 2, so I'll just add these two things. I'll say 0.2 plus 0.1 plus 0.2, so this is 0.5. Okay, so if I say probability x is less than equal to 0, so this will be 0.2. Probability x is less than equal to 1, 0.2 plus, you are just summing this up. So that's why it's called cumulative sum. So you might have done a lot of problems like this. If you have an array of this sort, 1, 2, 3, 4, 5, 6, 7, and 8, and if you are asked to calculate its cumulative sum. So how do you compute that cumulative sum? You have this array. Now what you do is, initially you say 1. Then once you are in 2, you are adding previous 2. You are saying 1 plus 2 is 3. Then you are adding these three things. If you are having this thing, 3 plus 2 plus this is 6. Then you are adding these things to enter the value here. So this is called as cumulative sum. So that's why this is called as cumulative distribution function. Okay, because we are accumulating these things. Probability x is equal to 1. x is equal to 0 is this much, probability x is less than or equal to 1 will be addition of these two things, then addition of these two things. So you can clearly see that this will be always increasing function, and not just increasing in terms of in discrete random variable, it will be a step function. So why step function? Because initially you will have from, let's suppose, 0 value, but then 1 value, then 2, then 3, then 4. So initially, let's suppose it was this. So once you move on to 1, it will suddenly jump till here. It will suddenly jump till here. It will suddenly jump till here. So you will see stepwise function in terms in this in discrete random variable, because associated with discrete random variable is a probability mass function, and because it takes discrete values, it does not take continuous values. So that is why you see these jumps. The probability, the value will take the variable will take value 0 will be this. So till this 0 to 1, it will be this much, let's suppose, and once you move to 1, so you'll suddenly jump till here. Okay, that's why you will see this as a step function. You will not see it as a continuous function. So when we will go to continuous random variable, we will see that we will not define PMF there. We will define what's called as PDF, probability distribution function, because this mass function has a problem there. So we have to redefine it. Any questions for on this? And one more thing that you can compute from the CDF, you can also now compute this. So if you have to compute probability that a random variable x has value between a and b, this is pretty easy to compute. So you can compute probability random variable will take value less than, let's suppose, a, and you can compute probability that random variable will take less than b, and then you can add, subtract accordingly to come up with this. So if you subtract these two things, so you will get this. Okay, in terms of Amazon delivery system or online e-commerce delivery system, you can say what is the probability that my order will reach between 3 to 5 days, something of this sort. So you can compute these two things, and based on this computation of these, so this should be b over here and this should be a over here. Okay, just a correction, because I have to see between a and b, so I have to first compute b and then a, because b is usually higher. So first compute this and subtracted a, and then you will reach this. So this again as a consequence of cumulative distribution function. Okay, the takeaway home lesson is that with random variable, discrete random variable, you have two functions defined. The first function was PMF, the second function was CDF. PMF is probability mass function. That means how do you distribute this mass? You can see probability as mass. How do you distribute to different of these possible values that random variable takes? Okay, second thing was cumulative distribution. If you have to cumulate it, and I also gave the rationale. What is it? Why is it called cumulative distribution function? Now you saw that if somebody asks you, this is a random variable, give me its distribution. So you can either give PMF and you can either give CDF, and you saw the connection between this PMF and CDF in terms of discrete random variable. Any questions still here? Any questions? Now you saw what a PMF is and what a CDF is, and you understood the notion. Why are they defined the way they are defined? PMF serves a purpose, CDF serves a purpose. And in order to just talk about distribution of any random variable, you can either define PDF or you can you can either define PMF for the discrete random variable and PDF for the continuous random variable, or and CDF for both of these random variables. Now we'll plot this PMF and CDF for maybe, let's suppose, some binomial distribution. Okay, so I'll take some initial imports over here. So I'll make the code screen visible. I hope this is visible. If you can see, this is normal imports, importing NumPy, importing matplotlib, and importing scipy.special for these combinations. I can also use NumPy's combination, but this is what I'll use. And the first thing is I'll use n and p, because you know there are two parameters. The first parameter is n, that is number of trials. If we have a coin, that is you're flipping coin 10 times, and probability of success. Consider this is a biased coin. So you can see that this p is equal to 0.3, that is probability of success is 0.3. So now I'll define PMF. So to define PMF, what I can do is I can say binomial PMF, because I need k successes out of n successes and with the probability p. So what can I do is I can just return this combination from this scipy. So I can just use the combination formula. Okay, this one. So return combination of n choose k, probability to the power k, 1 minus, this is not probability, n minus k. This is the general formula that we have seen, and this will give me the PMF. And similarly, I can define binomial CDF. Binomial CDF is basically sum till that point. Okay, that's what I have defined. Definition of binomial: k successes. This is till k successes. Like that means 0, 1, 2 till k, and out of n tiles, and p is the probability of success. So what I can do is I can just have this binomial PDF and then sum it till, let's suppose, till k. So I'm saying binomial PMF it starts from I and it goes till k plus 1. That means it includes k now. It starts from 0, 1, 2, 3 till k, and then it computes the binomial, and we keep on adding it. And these two, this is our PMF and this is our CDF. And you can clearly see that I derived this CDF from PMF. And now let's suppose I'll plot these things. If I take some values of k, because I have defined n, I'll take some values of k. So k value np dot range is 0 to k n plus 1. So it can be k can be 0, 1, 2 till n, that is till all the way. And now I can compute CMF, I can compute CDF, and I can compute PMF. So if I, the CDF values is this. So you have binomial, you take these k values, you take values from 0 to 10, inclusive 10, and then you are computing binomial PMF, and this will return, for each of these, this will return a number. So if I just print it over here, I'll print PMF values and print CDF value. So these are the values that are printed. These are the values that were computed. The PMF and PDF. Now I want to plot them. Okay. So plot and print. So I'll just copy this snippet of code and I'll explain you this so as to save time. So now we can clearly see I am printing the results over here. So this is binomial distribution, n is equal to n and p is equal to p, and then PMF is this and CDF is this. I am printing the values, and now I am plotting two figures. So one is of PMF, where I am plotting two subplots, because you know there are different ways of plotting. One is called as object oriented approach. So here you have directly used the direct procedure, not object oriented approach. So here you have plot the figure dot this, and subplot is this, and then this is the main line. This one over here. You are plotting bars. The value is k values, and you have PMF values. Similarly, you have k values and you have CDF values. CDF and PDF was computed over here, and then you are plotting it. You are giving it label, and then you are having grid. And I think we have done matplotlib extensively. So if I just run it, you can see this. Now I was telling you that CDF is a step function. If you see this PMF, so this is PMF, the probability that you will get, let's suppose 0 heads. If this is 0 success, 1 success, 2 success, 3 success, and it can be thought as also getting reviews. Okay, something like that. Now if you see, this is a step function over here. So this is CDF and this is PDF. Okay, so if somebody asks you, show me a distribution of random variable, you can either show PDF or you can give CDF. Both of these are mathematical things, but many of the times when you are even seeing a paper or something of that sort, you will see these figures made. You will see usually this is what distributions are called. So you will see majority of the time is this figure made. So this is distribution. So either I can give you a mathematical expression, I can give you distribution. Read correctly. So either I can write it mathematically, either PDF or CDF, or I can give a graphical representation. So usually it is easy to give a graphical representation. So this is what people usually mean by distribution. How do you distribute this mass? How do you distribute this probability mass? Okay. So I hope now these two diagrams, CDF and PDF, is clear. Any questions on this? Moving ahead to the question number 2. So the question goes like this: it is known that screws produced by a certain company will be defective with probability 0.01. Okay, and each is independent to each other. The company sells the screws in a package of 10. There is a package. Each package contains 10 screws. Okay, and offers a money back guarantee that at most one of the screws is defective. What proportion of the package sold must company replace? So you have to tell me the proportion of the packages that company must replace. Proportion of the packages that company must replace. Okay, and this is how this is the defective rate rather. So that screws produced by this company will be defective with this probability, defective with this probability. Okay, and the packages are having 10 screws in each of them. So they are offering a replacement guarantee, money back guarantee, if at most one screw is defective. Okay, so what percentage or what proportion of the packages should the company replace? So now if you see this question, we have to find the proportion of packages that company must replace. That is, how many packages will have at least 2 defective or more than 2 defective screws. Okay, now if you see this thing, sampling each of a screw is a Bernoulli random variable, because it can be either defective or it can be either good. I'll say good or defective, or success or failure. So each of that is a Bernoulli process. Each of that is a Bernoulli random variable. Now you have been given success is 0.09, defective is 0.01, and success is 0.99 then. Okay. Now what you have to do is consider a random variable x. X is a random variable which says that number of defective screws. defective screws. You can choose any random variable. I am choosing number of defective screws. You can choose number of good screws. Okay. So now you have to have the values that X will take. X will take value 0, 1, 2, 3 till 10. All the screws can be defective. None can be defective. 1 can be defective. 2 can be defective. Okay. Now I am interested in which package will be returned. The packages that will be returned will have 2 or more defective screws. 2, 3, 4 till 10. So these packages will be replaced, or money back guarantee will be given to these things. So these will be replaced. Okay. Now the possibility is I'll have to compute probability X is equal to 2, probability of X is equal to 3 till probability of X is equal to 10. I'll have to compute this. So I'll have to compute all of these. Okay, this is one way, but I know that what I can do is I can say probability of 1 minus, I can just compute the complement. Probability of 1 minus X is equal to 0 minus probability of X is equal to 1. So this will be easy to compute. So now each of this probability X is equal to 0, X is equal to 1, X is equal to 2, this is a binomial random process. Now if you see this, each of this is a binomial random process. So now here we have 0 successes, and here in binomial we have 1 success. So here I am considering failure as success, so I'll have to also flip the probability. So this will be 0 successes among 10 trials with the probability of 0.01, that is success probability of 0.01. Similarly in here, this is 1 success out of 10 successes with a probability of 0.01. Okay, now when I compute this will be 1 minus, I want 0 successes out of 10, and what is the success probability? That is 0.01. How many successes do I want? 0 successes. So what is the failure then? This is 1 minus 0.0, that is 0.99 to the power of 10, because I want all the things to be failure. So here I considered failure as being defective. No, sorry, here I considered failure as the success, actually, as the product being right, as the product being good. And now plus I want 1 out of 10, that is I want 1 success out of 10. Here success is considered a defective thing. So now the probability of being defective is this much to the power 1, and probability of being good is this much, but here we consider this as a failure to the power 9. Now when you add these two things together, so you roughly come out, this comes out to be, let me check, this comes out to be 0.04. okay, that means only 0.4% of package will have to be replaced. If you see this, we had to compute this. Basically we had to compute probability of X equal 2, probability of X equal 3 till probability of X equal 10, and then add them together. But we decided that we'll compute the complement of this, that is 1 minus probability of X is equal 0 minus probability of X is equal to 1. That means either we had to compute this addition of all of these, but the easier way was to go with the complement, and then we land at this answer. Pretty clear? So a bit of biology before going ahead. So the assumption is that, let's suppose a pair of genes is responsible for a particular trait. So here by the trait I mean, let's suppose color of eyes, or maybe let's suppose height of a person, or something of these sorts. So these are the traits. So let's assume that these traits are decided by a pair of genes. So now in genes we have two things. We have a dominant gene and a recessive gene. So what is a dominant gene? So a dominant gene is a gene which will always express if it is present either with its own counterpart or with a recessive gene. So what do I mean by that? Let's suppose we represent D by dominant and we represent this recessive by R. So now, as I said, and we assume that a pair of genes is responsible for a particular trait. So now the pairs possible will be DD, RR, DR, or RD. Okay. So here if you see these two things, so these are pure forms, either dominant or recessive. So the dominant gene here obviously will express. So in this hybrid case, now you have dominant gene with the recessive gene also. So now, because the gene is called dominant, because in this the dominant gene will express. That's why it's called dominant. So dominant gene gets expressed either in pure form or in the hybrid mode. So recessive gene only gets expressed when it is in pure form. So here recessive gene will express. So the express R will express this R, small, kept the small r, whatever. Okay, so this is a bit of background. So now the question goes like this. So consider that a particular trait such as color of eyes or left-handedness of a person is classified on the basis of one pair of genes, and suppose also that D represents dominant gene and R represents the recessive gene. Thus a person with DD, that is this, is pure dominant and this is pure recessive, and this is hybrid, or this is hybrid. The purely dominant and the hybrid individuals are alike in appearance. As I said, dominant gene will be expressed. That means that people who are either in hybrid form of the pure dominant, they'll have the appearance of the dominant gene. One more assumption, that let's suppose children receives each gene from the parents. Each one gene is received from one parent. Let's suppose here the children have two parents and they receive one gene from each parent. Let's now say we have two hybrid parents. The question goes like this: we have two hybrid parents. That means the parents are in this state. So you have father and mother and they are in hybrid state. Okay. Now the progeny possible is this, because one gene will come from here, one gene will come from here. So DD, RD, DR and RR. So here if you see this is one the same. So I can write it like RD, hybrid mode. Okay. Now let's suppose that these parents have 4 children. So 4 children are there. So these two parents, this and this, have 4 children. So now the question goes like this. The question goes like, what is the probability that 3 out of 4 children will have outward appearance of dominant gene? Outward appearance of dominant gene. Okay, now here this thing can be again seen as the binomial probability, because here each child, because getting a particular trait for a children can be thought as a Bernoulli random variable. It can be either a dominant or success, or failure or success. So it can be either dominant or recessive, failure or success, something of that sort. Now if you consider that random variable, so here the success will be having the outward appearance of a dominant gene. So we can consider X can be X is success, basically X can be success or failure in each of these things. So we have 0 or 1, that means dominant or recessive in here, and then we basically want to perform it for 4 trials, that is the binomial random variable. So 5 binomial random variable, among those we want 3 successes out of 4. So what's the probability that we have to compute? We have to compute here probability of success. Probability of success. The probability of success in this case will be the probability that the children has an outward appearance of the dominant gene. So this will be the probability of success, and then we'll have to compute it. I'll give you some time to compute it, then come back. Now let's do it like this. So this is appearance of the dominant gene. So now you know both the parents are hybrid. That is like this. So when we'll make progeny, so there is a possibility of this. Either they'll have RR, and we know each of the genes is, let's suppose, independent. So we'll have RR, and this RR. So this is the same. This is hybrid case. This RR and RR is hybrid case, and this is pure recessive and pure dominant. So now we have 4 possibilities. So each has 1/4 probability. So this has 1/4, this has 1/4, this is 1/4 probability, this is 1/4 probability. Now in both of these conditions, or in rather 3 conditions, the dominant gene will sort of express. So now the expression is 3/4. Dominant gene will express in 3/4 condition, and recessive with 1/4. So now think it as success and failure. The question was, out of 4 children, 3 should have the dominant gene. 3 should have the dominant trait rather. Okay, the brown eyes, let's suppose. So we are thinking this as success and this as failure. Now 3 out of 4 children should have the dominant trait. Should have the dominant gene trait. So now you see 4 out of 3 we choose it like this, and now success probability is 3/4. So for how many people do we want to succeed? For 3% out of 4. Then for 1 we want the failure, because this problem can be again modeled by using binomial probability. So you have 4 basically means 4 trials, 3 means 3 success, and probability of success is 3/4. So how did we compute this? So we computed this by using the simple principles of genetics. And here we also assumed independence. We said that each gene is independently contributing to it. So that's why we made 4 combinations, and now we saw that this RR has combination 2/4 and this has 1/4, 1/4. So overall the dominant appearance will have 3/4 probability. So that success probability will be 3/4. So if you compute this comes out to be 27/64. Okay. Hence the answer is that whatever the question was, what is the probability that 3 out of 4 children have the outward appearance of dominant gene, that is 27/64 is the probability of that. Okay, so one more takeaway lesson is that sometimes you will see that both the parents are brown-eyed, but you will see a blue-eyed baby getting born. So why is that? So it is because of this, because they are having hybrid. Maybe in their what I can say, in their generation or in their parents or grandparents, somebody had blue eyes and the genes were still present in their DNA, and when they were passed on to the child, and now let's suppose if we consider blue eyes to be the recessive gene, and then the child got the pure recessive gene, they got pure RR, let's suppose in this case they got this condition, and that's why there is a possibility that if there are two brown-eyed parents, they can have a blue-eyed baby because of this gene transfer, because gene transfer happens a different way and which will express depends on many factors. Okay, and that's why you see sometimes the traits which are not in appear in the parents, they are in their children. Why? Because of this, because they are in hybrid mode. Probably they still are there, but dominant gene is expressing in their parents, but when the children is getting those genes, their recessive gene is expressing because maybe it is present in the pure form. Okay, and the same concept also applies to blood groups, because you have blood groups A, B, O, and then you have positive, negative, and then you have blood groups A, B, you have A, B, and O. So these are the 4 blood groups positive. Then there are 2 more things. There is a rhesus factor, plus and minus. So that means is rhesus factor present, that means positive. If it is not present, that means negative. And then if people have, let's suppose, A and O, so here A is dominant. If other person has, let's suppose, B and O, so this B is recessive always. Okay, and then let's suppose if these 2 people got married, and what is the blood group possible? The blood group possible will be A and O, because you can get O from here and A from here. B and O is also possible. AB is also possible, and O is also possible. Okay, then blood group will be A, B, AB, or O. These are the blood groups possible for the children. Okay, and then it depends on rhesus factor also. If let's suppose both of these parents do not have rhesus factor, then it is sure that nobody will get rhesus factor. That is, nobody will be positive blood group. And if somebody one has and one does not have, let's suppose, so there it is sure that each of these will have positive factor, because at least one parent has it. Okay, this is the genetics of blood groups. Okay, and from blood groups you can easily know, if you know the parent blood group of your parents, you can at least come to the conclusion what is the blood group, what is the possible blood group that you have. You can at least negate the possibilities. So here, if your parent had, let's suppose, pure A blood group, something like this, and your father had this, and your, let's suppose, mother had this. Okay, now the possibility of you having blood group is only A, because why? A will always, you will either have AA or AO, A from here, O from here. So you will always have blood group of A, something of this sort. So it depends on what your parents have. So you can evaluate the conditions accordingly. Just a side note. Any questions on